So today we're carrying on in Thermodynamics of Energy and Mineral Engineering with topics related to Chapter 1. We're still in Chapter 1. I do need to remind you, though, that your homeworks are due in standard report format specified on Angel. That would be on the pale green gridded engineering paper, much like the background of this display, but in green, and only with your work only written on one side. Follow the instructions to the detail, and you'll do just fine. Each homework is, again, 1.25%, very small weighting for each homework, but it's practice and the skill that you develop from that will be important. They're due at 4 p.m., handed in stapled with your name and all the attribution associated with it in 110 Hostler. A box will be out there, and you will be required to sign off that you have dropped off this homework. All right? So let's carry on with today's lecture. Now, one of the uses of thermodynamics that had been spoken about in class is to use thermodynamics as a code breaker. Thermodynamics for code breaking really is carried through with what we'd call an equation of state. Now, there's a language aspect, equation of state, that is pretty important inside of thermodynamics. I'm going to just pause for one moment and just remind you all that you're more than welcome to pause, take notes as you go along, and you can time things really nicely as we move forward. Okay? So, we're going to start in thermodynamics with gases, and we're going to think of the ideal gas model. And the ideal gas model is really defined by an equation. PV is equal to nRT. That's it, over on page 13 of the Koretsky textbook. That's equation 1.9, where we just isolate one of the properties, pressure. Pressure can be described in terms of number of moles, the ideal gas constant R, the temperature of the system, and the volume of the system. Okay, that would be number of moles in the system. Oftentimes in these early descriptions, we're going to be talking about closed systems, so there's N stays fixed in many of our early problems, right? So, considering that, there are requirements for the ideal gas model to be valid. Essentially, the underlying theory is that the gas molecules will occupy negligible volume. They're assumed to be so small relative to the system space that they're in that they effectively occupy no volume. And they have no intermolecular forces, meaning that each molecule doesn't know of the existence of the other molecule around it, barring a coincidental collision. But they're not drawn to each other by electrostatic forces or short-range forces that we think of later in the semester. So, we're only thinking about gases. This is code breaking for gases. In the ideal gas model, there's no condensation process. There's no way to make an ideal gas in the model form condense. Why would we say that? Well, if we think about it, we have no intermolecular forces, no forces of attraction. And if I have no forces of attraction, I have no ability to actually cause a bond to form or to cause my gases to condense. So the ideal gas model is really meant to fit a model of the system under which you don't have a condensation process. You don't have a transition from a vapor to a liquid. Okay? The majority of your kind of beginning work in solving problems are going to be dealing with intensive variables, in this case pressure and temperature. You see that volume is in equation 1.9, but that's not going to work for us. We'd like to convert that into an intensive property, and so we create it as molar volume. And again, this is where V bar in my notation in the notes here is signifying the same thing in Koretsky, that is just the lowercase v. And that would be the extensive volume divided by the number of moles in the system of that component, K. So, how many intensive variables is it going to take to basically specify the energy address, the state of a system, you know, given that I have a pure substance that's behaving here according to an ideal gas behavior. Well, it turns out we have that answer in page 17 and 18. It's called the state postulate, right? And it says that for a system with a pure substance, meaning like pure nitrogen or pure H2O, the thermodynamic state, the energy address, and all the remaining intensive thermodynamic properties can be described using, or can be determined using just two intensive properties. So if I have one phase, meaning only a gas, phase, and if I have a pure substance, one component, meaning just H2O, not H2O and oxygen, just H2O, or just nitrogen, I can use the state postulate and determine the entire energy address for the system with two intensive properties. That's the real power of intensive properties, is they are actually unlocking the energy state, the state of the system. So here we have it. Pressure and molar volume are going to be used to determine temperature. So if I have a known molar volume and I change the pressure of the system, then I can know the temperature of the system. If I have a known pressure and for some reason the molar volume changes, oftentimes that would be because the mass changed in the system, then the temperature would be changing. And of course the gas constant is a constant, so it's just a numerical coefficient going along with the rest of the equation. And so this is code breaking with an equation of state. If I want to know temperature and I only have pressure and molar volume, I can find it. I don't have to measure it to find it. Very powerful stuff. All right. So, following up on that state postulate, we are thinking of turning the problem around. This is where thermodynamics gets a little bit circular, right? We can think of molar volume mathematically as a function, like V, or V bar, is a function of temperature and pressure. It is an intensive property, but it can be defined as a mathematical function, or we can put V on one side and put an equation on the other side, right? So contrast that to the actual extensive volume, which is a function of temperature and pressure and number of moles in the system. That would be an extensive property because it one of its functions, one of its properties is dependent upon the number of moles, the quantity of something. And so that one more thing is a variable. If I were to look at this in terms of math, in terms of the way that we'd be thinking of this, the temperature, pressure, and number of moles would be independent variables for my function, and volume, extensive volume, would be my dependent variable. Now, temperature and pressure, as we've said, are also intensive, but we've got some language terms, Tsat and Psat. These are saturation. Saturation is just a thermodynamics language-based way of talking about that point right at the boiling point, or that point where water is transitioning, liquid water is transitioning into vapor water, or vapor water is transitioning into liquid water. We call those Tsat and Psat. And if you look in table B1 and B2, those are saturation tables. They tell you saturation on either side of what we call the vapor dome. So if I go from vapor in a process is, in thermodynamics, process is another key word. This is language. Condensation is a process, and condensation is a process where I go from a vapor to a liquid. And we know that the opposite of that is evaporation, where I go from a liquid to a vapor. Both of these processes occur at a saturation state, somewhere on a boundary between phases. And so I'm going to have you think about saturation temperature and saturation pressure. Maybe write those two down and go up and look up what is saturation temperature, what is saturation pressure. Basically, we're talking about boiling point. A boiling point temperature and a boiling point pressure. That's Tsat and that's Psat. So, saturation condition, it's a threshold to phase change. It's another way of looking at it. Saturation is a threshold to phase change. And that phase change threshold in thermodynamics, when we're talking about vapor and liquid, would be called the vapor-liquid equilibrium. And there it is again. Tsat and Psat represent the boiling point for the vapor-liquid equilibrium. All of these things that I'm going across are just bundled up with key language terms. The thermodynamics of this is very easy. The skill of understanding variables as independent variables and dependent variables and variables tied to state functions, that's a skill. And a process, the VLE, the vapor-liquid equilibrium, saturation temperature, saturation pressure, state postulate, those are all language. Things to be writing down, to be bringing into your long-term memory, not short-term memory, long-term memory. So here we have figure 1.6. Once again, feel free to open up your textbook, take a look at figure 1.6 in detail. This is, water-ish. This looks a lot like a water diagram, but it's not exactly water, just based on the way that the solid-liquid line is on that pressure-temperature diagram in the lower right. Feel free to look up pressure and temperature relationship of water on, like, say, Wolfram Alpha. Wolfram Alpha is a great web resource for these things. But this is just giving you like some generic fluid that has a transition between a liquid and a vapor. And you notice that the top plot has three variables: pressure, volume, and temperature. Three axes, three variables. Any spot within that phase space, that space is that inside of that imaginary cube would be called a phase space, is going to be a state. Any point is a state. So the critical point is a state in the system that we are looking at. We need to specify a state first, so let's work through these diagrams by specifying a state 1. So okay, there's state 1 on my pressure-temperature diagram. You see that it's existing on the vapor-liquid equilibrium line. There's a line between which vapor and liquid are in equilibrium. I can translate that pressure-temperature state, which is a point, over to the pressure-volume diagram. Now let's do that next. Oh yes, that's right. I need to point out that there is a Psat and a Tsat existing where that point is. We're just going to assume that this is, for now, pure water, even though the diagram doesn't quite represent that. And I am representing it with two intensive variables, Psat and Tsat. Okay, now let's see if we can translate that. Oh, yeah, that's right. We are actually know that the state is an energy address. So far, our only energy function has been internal energy, which is the capital letter U, or the lowercase letter u if we were intensive, and it's a function of molar volume, of pressure, and of temperature. All right, there's the translation of that same point onto the pressure molar volume diagram. You see, I've got pressure in the on the y-axis and a lowercase v, which would be v bar in our notes, for the molar volume. That point becomes that line between that liquid vapor dome. That's a liquid vapor dome in pale gray. And so you have a line, that red line that I've listed as an isotherm, where everything is at constant temperature along that line. Anything on that line is at the same temperature. Underneath that vapor dome, that little horizontal tie line, that is where Psat and Tsat are defined. So even though temperature is not explicitly defined, it is constant under the vapor dome there. And I have my 2 points, my 2 end members along that tie line between the vapor dome left side and the vapor dome right side. That would be my saturated molar volume of the liquid on the left, saturated molar volume of my vapor on the right. Again, same temperature, different fraction of molar volume versus of liquid versus molar volume of vapor. The process, right, at any vapor-liquid equilibrium state, the process, if we were going from left to right, would be evaporation, right? I'm going from a liquid at a saturated liquid where there's effectively 100% liquid just on the edge, about to boil, at 100 degrees Celsius, let's say, at atmospheric pressure, just at that threshold of boiling, but no vapor. And then we go from left to right, and as we go from left to right, we have an increasing quantity of vapor in the system. So the phase is changing from liquid to vapor. And I go to state 2. And if I go from state 1 to state 2, that is a process. To go from state 1 to state 2, from a beginning state to an ending state, that language-wise in thermodynamics, that's a process. So there's some key states in here that are where temperature and pressure are not independent of each other. That would be at the critical point and at the triple point. And you see that both the triple point and the critical point are both basically dots. In this case, well, it's a triple line in this case, but the critical point is the key point that we think of. It's the one that we look at, and in table, I believe it's B1, the temperature table, where you go to the top, you go to the bottom of that table, and you're going to see the critical point temperature and the critical point pressure. It's the highest temperature and pressure you can get while maintaining these phase relationships, and that's the point where the molar volume or the specific volume of the liquid is equal to the molar volume or the specific volume of the vapor. Look at that table. Go to the bottom of that table. Look it up. See those two values the same. It's a part of your homework anyway. You should know how to look at the diagram here and connect what you're seeing in the diagram to the table, because they're the same thing. All right, look at that last entry. Table B1. That's on page 649 of the Koretsky book. So we're talking about phase change. You can look at the saturation tables to better understand phase change. Big part of what we're doing in our homework. We understand that we're using the vapor-liquid equilibrium relationships to do code breaking, to understand different state variables or the state of the system, the energy address of the system, using fewer variables, and to measure a few variables and then ultimately understand the whole system. So how else would we look at that? Well, a phase in the textbook would be either P or pi, and that is essentially the phase in a language term in thermodynamics is going to be the stuff that is homogeneous in chemical composition and in physical state. So ice is chemical composition H2O, the specific ice, say, in our freezers, and the physical state of ice is its crystalline form of a certain crystal structure and has bonding in a certain way, and all of that is homogeneous across the entire, say, ice cube in your freezer. Very different from the phase of H2O, chemical composition of H2O, when it's in the liquid state, physical state, and where the bonding is very different, not crystalline bonding. And so that would be phase. Now, there's another term that pops up. It's called component, and we give it either a C or an M. M, I think, is in your textbook. It's basically a chemically independent constituent of the system. So H2O is a component. Oxygen is a component. Nitrogen is a component, say, in the atmosphere. They're each chemically independent of each other, even though so this is where we don't go all the way down to just carbon, just nitrogen, just oxygen, and hydrogen. We have H2O, CO2, O2, and nitrogen. These are like chemically independent constituents of the system, are called components. And we're leading to somewhere in terms of code breaking here. And that is a universal kind of application called the degrees of freedom. Now, the degrees of freedom, don't let it get you into like deep philosophical thought. Degrees of freedom mean something very pragmatic. Okay, it means in our case, it means the number of intensive variables. Remember, intensive variables in a system that are independent of one another. How many intensive variables are independent of one another? Okay, we're going to use this in what's called the Gibbs Phase Rule. So you saw the state postulate earlier. It's in your reading. I want you to go to look at equation 1.12. I've modified it to turn it into an equation that's a little easier to read and frankly more modern than what your textbook has, which is just your degrees of freedom F is equal to the number of components minus the number of phases in your system plus 2. It's going to be an important equation. F is equal to C minus P plus 2. That's a good one to start writing down and memorizing. There's not a lot of things in this class that you're memorizing. And in fact, this type of equation would probably be on an equation sheet in an exam. But it's a good thing to start getting into that long-term understanding. So the Gibbs Phase Rule it basically tells you how many intensive variables do I need to describe the state of a system. Well, if I have one component, like H2O or nitrogen gas, and it's a single phase, right? Let's see, 1 minus the number of phases. Let's say I have one phase. My degrees of freedom is 2. So I have 1 minus 1 plus 2, right, is going to be 2. Or if I add 1 plus 2 and I subtract 1, I get 2 degrees of freedom. Well, that's the state postulate. If I have one component in one phase, 2 intensive variables will describe the entire state. Great. Aha! Let's look at it a different way. If I were to have, if I have nitrogen in the air, I just need pressure and temperature, and I can define the entire state of the system, which is great for, say, meteorology conditions. If I had two phases, let's say I had water vapor and water liquid, the vapor-liquid equilibrium, well, then I'd have one component minus 2 phases, one component H2O, minus 2 phases, the vapor phase and the liquid phase. This would be happening just as I'm boiling water inside of a system. Let's not assume that I have an open pot, but let's assume I was boiling water with like a closed kettle of some sort. Then I would have 2 phases inside the system, closed system, energy still can cross the boundary. One component minus 2 phases plus 2 leaves me with one, just one intensive variable that is needed to be independent of one another, right? And in the liquid-vapor equilibrium, you only need to specify temperature or pressure, which is exactly why tables B1 and B2 in the back of the book only require the furthest left either temperature or pressure to define the entire system for the internal energy, the entropy, for the specific volume of the vapor, specific volume of the liquid, all defined using only one variable. This is a really powerful part of thermodynamics, thinking of thermodynamics for code breaking. Okay. So here we have a figure from the example 1.2. This is another reason why we use this textbook, is because it does contain numerous examples throughout, which is very helpful for engineering students. You'll see the vapor dome. This little humpback shape is the vapor dome. This is a pressure molar volume phase diagram. You're looking at PV space is another way of looking at it. In thermodynamics, we talk about the space in a plot as like we defined according to the variables on the axis. So this would be PV space. So under the vapor dome, right, we have both a liquid and a vapor. We have 2 phases going on under the vapor dome. Outside of the vapor dome, we have one phase, either liquid or vapor, right? And up at the top is that dot. That dot is, of course, the critical point. Okay, so let's take a look at this. How do we determine the proportion of H2O in each phase when we're under the vapor dome. It's basically a number line or a tie line where we have to know the fraction in between. That fraction in between the tie line is called the quality, X. It's a value from 0 to 1. Okay, this is not a percentage, this is a fraction. We're in engineering, we use fractions, we don't use percentages. So 0 to 1, quality, X. And so there's my isotherm, where my temperature is already stated. I see that I'm at constant pressure across the horizontal line under the vapor dome. And so if I look at page 19, equation 1.4, I'm going to see that one of the several ways of defining the quality is the number of moles of the vapor phase divided by the total number of moles in the system. Okay, the number of moles of, say, H2O that is only in the vapor phase relative to the total number of moles in the system. It's a pretty clear fraction. It's going to be somewhere between 0 and 1. I can look down here in the equation that I can rewrite this as again, thinking along the number line. Where am I on that line? That's that first numeral V for my molar volume, minus the saturated molar volume of the liquid in the numerator. Right? So that's basically the length of that short distance on the number line from VL to where it's the fraction of vapor says 0.2 on the diagram. And then the denominator is just basically what is the total length of that number line. The total length would be VV minus VL. And I can use any intensive property to actually solve for quality. Here I've just happened to be using molar volume. And a lot of the times we think of this like as a fulcrum on a lever. I like to think of it as a number line or a tie line where I have the molar volume of the liquid on the left. That's kind of the low energy value, and then the molar volume of the vapor on the right. All those plotting in there. V1 is plotting right into that V space on the equation to give us a quality X of 0.2. So if X is going to be from 0 to 1, we would actually practically call high quality steam something that has a quality from, say, close to 1. 0.8, 0.9, near 1 is a high quality steam. High quality steam ends up being a very useful term when we're trying to run a turbine. So if I use steam to spin a turbine, I need high quality steam because essentially water droplets in low quality steam will actually hit the blades on the turbine and will actually cause abrasion on the turbine. They'll pit the blades and etch away, slowly physically etch away the coating on a turbine blade, and thereby leaving the metal open to corrosion. So the high quality steam doesn't have that physical pitting nature to it, and so there's a longer term value to turbine blades with that. So saturated vapor on the right hand side of the vapor dome, saturated liquid on the left hand side. Of course, we've got regions to the left that would be called subcooled liquid. Regions to the right of the vapor dome on the right side would be called superheated vapor. These are all language terms. Feel free to pause, go back to your book, take some notes. Subcooled liquid, superheated vapor, and saturated liquid versus saturated vapor right on that vapor dome line. And of course, the isotherm is that vertical, then horizontal, then sloping line. It's the line at which the temperature of the system remains constant. Here is my critical point, and the critical point is pretty well defined by the partial change in pressure with respect to the partial change in molar volume at the critical point temperature. That derivative is going to be 0. And then the second derivative is going to be 0 as well. That is mathematically how we would define what is the critical point. It's a factor of pressure and molar volume change. Okay. So, last comments that we're thinking about here is that quality, very important term, very useful term for a big chunk of what we're going to do in the half of the semester. Quality is basically another form of interpolation, which is a skill. Quality as a term is a language. That is linguistic in thermodynamics. We want to know what quality means. We develop our skills with interpolation, with quality calculations from the tables. Got a lot of language going on in this first arc of development. And we've talked about the language of the vapor-liquid equilibrium. Can't get around the vapor-liquid equilibrium. That is a language term. Phase change, degrees of freedom, intensive properties. Intensive properties are the number of intensive properties that I need to describe the state of the system is defined by the degrees of freedom, which really tells us a lot. So all of this leading to the thermodynamic component of this, which is code breaking, both for a ideal gas scenario where I've only got one component and I have no condensation, and for the vapor-liquid equilibrium scenario where I can have the possibility for intermolecular forces and ultimately can have condensation and evaporation happening. Okay, I think that's it for us today. Again, welcome your questions in class. I welcome you to stop by for office hours. That will be occurring from 2 to 4 on Mondays this spring semester of 2016. And otherwise, I hope you have a great time this semester. Thanks so much.